welcome. We are studying digital frequency meter. So far we have seen that a frequency meter is nothing but a counter. Okay. It is basically a counter and you give the input signal to the clock of this counter. It can be either positive edge triggered or negative edge triggered. Okay. But if the input is not square or rectangular, then you have to first convert it into a square or rectangular wave. So, you can use a Smith trigger. Okay. So, this is a Smith trigger. So, you give the input first to the Smith trigger and you feed the output here, but you can also use the AND gate, so that you have a flexibility to stop the counting at some point by making, say, this input G of this AND gate equal to 0, you can stop passing the input from here to here. So, the counting will stop. Okay. So, this is the input, this can be a sine wave or anything. Here we have a square wave and this will count. Then okay, we may need a reset. Input to reset the counter value to all 0 before we start counting. Okay. So, this is the basic scheme. Now, let us talk about time period measurement. Okay. So, previously we have talked about frequency measurement. Okay, where we count the edges of the input or the received input, edges of input signal for a predefined time. And that predefined time is controlled by this gate signal. Okay. So, here you give a signal like this, which is 1 for some time and then it is 0. Okay. So, this is the interval where the counting occurs. So, this is this predefined time, which we call the gate time. Okay. So, let me write gate time. So, this predefined time is called gate time. You can also call it as counting time. Okay. So, we count this signal or the pulses of this signal within this gate time. Now, let us talk about time period measurement. Okay. This is also called reciprocal counting. Okay. So, this is also called reciprocal counting. Why? Because firstly, you know that time period is reciprocal of frequency. Okay. So, time period is 1 over frequency. So, that is why it is called reciprocal counting. And what do we do here? We will count the number of cycles of a known frequency signal or a reference signal of a reference signal, reference square wave within one cycle of input signal. Okay. So, here we count the okay, let us write cycles. In frequency measurement, we count the number of cycles of input signal within a predefined time, and here instead of counting the input signal, we count another signal, a reference signal with known frequency. Okay. So, we count another different reference signal within one time period of the input signal. Okay. So, reference square wave with known frequency. Okay. So, let me draw the two things side by side to make it more clear. So, normal counting versus reciprocal counting. Okay. So, in this case we measure frequency measurement, and here we measure time period. Okay. So, what we do, we have in either cases we have two signals. Here this is say input signal, okay, and so this is input, and we have another signal which you call the gate or G. This is on for a time and then it is off, okay, or like this. Okay. In this case, you count the number of cycles of this signal within this one cycle or half cycle of this gate signal. Okay. So, count input cycles within one gate pulse, gate cycle or gate time, whatever you call, which is this. Okay. So, this is gate time. Okay. So, within this you count the number. So, in this case the count is how much? So, starting from here I have one cycle, two cycle. Okay. So, roughly, so I have two cycles of input signal within this. Now, I need to know this gate time. Okay. Gate time is known. So, therefore, I can write this frequency f is equal to the count, which is 2, divided by gate time. Gate time. Okay. If say gate time is equal to let us take this is equal to half second or say 2 second or say half second. Okay. In this case count is equal to 2, 1, 2. So, count is equal to 2. So, frequency will be 2 by half, this is same as 4 hertz. Okay. This is normal counting. And what do we do in reciprocal counting? In reciprocal counting, let this be the input signal, this is input. Okay. We will have a reference signal which is of much higher frequency and known frequency like this. Okay. Say its frequency is known, or its time period is known. So, say time period is equal to T r, r for reference. Okay. So, this reference signal has a time period of T r, and we will count the number of these cycles within, say, this time. Okay. So, this is counting time, and here say we have 1, 2, 3, 4, roughly 4 cycles of the reference signal within this half cycle of the input signal. Okay. So, that means this time, okay, so this time is how much? If I call this T, okay, then T I can write this is equal to 4 times T r. Okay, 1, 2, 3, 4. So, this is equal to 4. So, 1, 2, 3, 4, it is slightly less than 4, it is not complete cycle, okay, or maybe, yeah. Okay. So, and what will be the time period of the input signal? So, for this, so input time period is therefore equal to 8 times T r, assuming that the duty cycle is 50-50. That means, this is 50% of the total period. The period is from here to here. So, this is the, so from this is one time period, right? And if so, if we assume that duty cycle 50%, that means this time is same as this time. So, if I have 4 counts here, so I will have obviously 4 counts here. So, then I can say, okay, the time period is 8 T r, where T r is the known time period of the reference signal. Okay. So, this is the difference between normal counting and in reciprocal counting. In normal counting, we count the input signal within our within the on time of gate signal, and here we count the reference signal within this on time of input signal. Okay, opposite. Okay, that is why it is called reciprocal counting. And okay, you may ask, what if the input signal is not of 50% duty cycle? Okay, so this is a small interesting question. If input signal does not have 50% duty cycle, okay, it's like this, say long on time and short of time. Okay. So, then we cannot simply multiply by a factor of 2 and get the time period. Okay. So, what can we do? The trick is simple. Then you take this input signal and pass it through a flip flop like this. So, let us take a T flip flop with toggle set to 1, and here you give the input to the enable. Okay. So, this signal you give, this input you give to the enable. Now, what will happen? How the output will look like? The output Q will change at every rising edge, right. This is a positive edge triggered flip flop. So, at every rising edge Q will change. So, if I draw Q, here on the same axis. Okay. So, say Q will change from 0 to 1 here at this rising edge, then it will change here at the next rising edge. So, Q will change like this 1, 0, like, and so on. Okay. So, this is Q, this is input. So, now you see the on time of Q, okay, is same as the time period of the input signal. Okay. So, this is time period of input signal. Okay. So, for one time period it will remain on, and for the next time period it will remain off. Okay. So, it is like this. Okay. So, therefore, if I use this Q as and measure the number of reference cycles. Okay. So, if this is my reference signal, which should be of much higher frequency. So, now you count the number of reference signals within this time. Okay. So, how many do we have? 1, 2, 3, 4, 5. So, count is equal to 5. Okay. And if this time period is TR, this is reference time period, then input time period is how much? Same as this, which is same as 5 counts of the reference signal. So, 5 times TR. Okay. So, we can use a flip flop like this before this input. I mean, so this input will be passed through this flip flop, and then we can use it. Okay. So, in this case, if I draw it schematically, so I will have this counter, and it will have this reset input to make it 0 initially, and of course, this clock, this is most important. But now it will count not the input signal, it will count the reference signal. Okay. So, here, so I will have this reference signal. So, this is the reference signal, reference square wave of much higher frequency than the input signal, which will come here. But you have to have the mechanism of stopping it. So, I need this AND gate. Okay. So, I put this AND gate here, and the other input of the AND gate will decide how long or for what duration the counting should continue. Here I will give the input signal. Okay. Maybe not directly, maybe through this flip flop. So, Q, let me draw it like this, Q, T, this is T, which is set to level 1 always, and here I will give the input to the clock. this will be the input signal. And okay, if you have an input which is not rectangular, you may also need schematically drawing a Smith trigger before this. Okay. So, you give the input here, which can be a square non-square wave like this, and this is also, you see, not half wave symmetric. So, therefore, after this Smith trigger we will have a waveform here which will look like possibly this. Okay. And after this we will have a waveform which will be like this. This time, if it is, call it t, this is same as the time period here. So, this is one time period, this is t, which is same as one time period here. This will also be t. Okay. So, you give, first you make the input to a rectangular one, then you can use this flip flop, and then within one period of the input you count the number of cycles of this reference signal. This is how it works. So, this is reciprocal counting. Very much similar to the normal counting. The only difference is the role of the input and the reference is reversed. Okay. So, here we are counting the reference signal within one period of the input, and in normal counting here we are counting, this is the input recept, we are counting the input signal within one period of the gate signal. So, these two change their roles in normal and reciprocal counting. Okay. Now, let us talk a bit about the errors that we may encounter in frequency measurement. There are normally two sources of errors that I can think of. So, two reasons of error. Okay. Number one, so how do we measure say frequency? Say in normal counting, consider normal counting only. Okay. So, we measure the number of input cycles within one gate time, and this gate time is known to us, right. We need to know this gate time. But say if we do not know this gate time precisely, then what will happen? We are measuring frequency with this expression, right, count by gate time, number of cycles by gate time. But if gate time is not known precisely, say we know this gate time to be half second, but say it is actually 0.49 second. In that case, we will have an error, right. So, and this gate signal is normally generated from a clock generator. Okay. So, we can have like a crystal oscillator, from which we can, after that this we can have a frequency divider, say this crystal oscillator has a frequency of 1 megahertz, that means the time period is 1 microsecond, which is too small. Now, I will talk about frequency divider later separately. So, say the task of this frequency divider is to simply divide the frequency of this signal. Okay, say if this is 1 megahertz, it may bring it down to say 1 hertz. Therefore, this time period, so the time period of the gate signal will be 1 second. Okay, then this time will be half second. Okay, but if this crystal oscillator is not oscillating at 1 megahertz, but it's oscillating at a frequency of 1.00001 megahertz, then this time will also not be half second, it will be somewhat less than that. So, therefore, we will have an error. Okay. So, if the crystal oscillator or the clock generator, whatever you call, clock generator frequency is erroneous, so this could be one reason. But normally crystal oscillators are quite precise. The errors may be like of the order of an 0.001%, too small. Okay. So, but depending on the input frequency, this may affect or may not affect. The another reason which we will talk in more detail is this. So, what we do? So this is my gate time. Now, I draw it with a larger span. So, this is the gate time or counting time, and within this time, so this is the gate signal, okay, and within this time we measure the number of cycles of the input signal. Okay. Say the input signal is like this, which has 1 period, 2 periods, 3 periods, and so this is 1, 2, 3. Say it has 3.5 period within this time. Okay. So, starting from here to here, we have 3.5 cycles. This is input, right, and this is fed to the counter, but the counter cannot display you 3.5, because counter is always incremented by a factor of 1, by a count of 1. Okay, and say it is incremented at every positive cycle or negative cycle. Okay. So, then the actual count that we will have in this case is 1 if it is negative edge triggered, 2, 3, and is it there or not? Okay, it is doubtful. So, let me take 2 cases. Let me just take 2 cases. One case is this, where I move the input signal towards the left a bit, okay, so that this starts from here. Therefore, this edge will also get included. Okay. So, then this edge will also get included. So, this means we will have count equal to 4. You see 1, 2, 3, 4. 4 edges are within one gate cycle, one gate time. Similarly, if I have the input signal starting from here at this point. Okay. So, this is the gate time. Then you see this edge is outside the gate time, this edge is also outside the gate time. We have 3 counts, 1, 2, 3. So, okay, we have count equal to 3. Okay. So, depending on where does this input start from with respect to this gate time on which we have no control over, we can get a count of 4 or count of 3, right. So, when we do not have integer number of cycles within one gate time, like this, we have 3.5 cycles, not 3 cycles, not 4 cycles, 3.5 cycles. Then the count, then the actual count will depend on where the input cycle starts with respect to the gate time, with respect to gate signal. Okay. So, this is gate signal with respect to this, is it starting here or is it starting here? Depending on that, we can have 4 count or 3 counts. Okay. And therefore, this will give me some error. Okay. Say this gate time is 1 second for simplicity. We actually have 3.5 cycles within this time. So, the true frequency is, so actually we have 3.5 cycles, implying true frequency is equal to 3.5 hertz, but the count is equal to either 4, implying estimated frequency or measured frequency will be equal to 4 hertz, or the count can come out to be 3, implying estimated frequency or measured frequency equal to 3 hertz. In this way, we can have an error. So, the error in this case, in either cases. So, here also we have an error of half hertz, 0.5 hertz, here also we have an error of 0.5 hertz, 0.5 hertz. Now, let us take a case where, say, an example where the gate time is equal to 1 second and input frequency, true input frequency is equal to, say, 9.9 seconds, 9.9 hertz, right. So, what will be the measured count? So, the count can have actually 2 possible values. Okay. So, the count should be within 1 second, it should have 9.9 cycles, but 9 cycles cannot be counted. We will count either 9 falling edges or 10 falling edges, depending on where the input starts. Okay. So, the count can be either 9 or it can be 10. If the count is 9, then what will be the estimated frequency or measured frequency? What will be our estimate? We see 9 count in 1 second, so estimated frequency is 9 hertz, right. In this case, we see 10 counts, so we will estimate the frequency to be 10 hertz. And in this case, how much will be the error? The error will be 0.9 hertz, 0.9 hertz. In this case, the error will be 0.1 hertz. So, what can be the maximum error then? The even say the maximum error could be, say, when you think that this is equal to 9.999. Okay. The true frequency is 9.999, but the count cannot be 999, count can be only 9 or 10. If it is 9, we will have a error estimated frequency of 9 hertz, and then the error will be 0.999. And if the count comes out to be 10, then the error will be finally 0.001. Okay. So, in the worst case, we see that we can have a count value which is almost 1 greater than or less than from the expected count. Okay. Okay. So, in this case, expected count was 9.999, you can put few more nines, and measured count is 9 or 10. So, error in count is almost equal to 1. If it is 9, it can be, so at max. Okay. So, at max we can have a error of 1 count. Similarly, another example, let me just modify it a bit. Okay. So, get time say 0.1 second, and say in true input frequency is 100.001 hertz. So, how many counts do we expect in one get time? Expected count in one gate cycle is how much? This is this is the frequency 10.001 hertz, multiply it with the time which is 0.1 second. This comes out to be 10.0001. This is the expected count, but what will be the actual count? Count cannot be fraction. Okay. So, the measured count will be either 10 or 11. So, how much error will we have? So, error in count. So, if it is 10, then the error is okay, very 0, almost 0. So, let me write it almost 0, 0.0001. So, that is very small, 0 or okay, let me first write the true value and then I will do the approximation. So, this is 0.001 or 0.999 something, and this too you can approximate it as almost 0 or almost 1. So, we can always have an error of 1 count. So, we can have an error of plus or minus 1 count at max. Okay. In the previous two examples, in the second example, if the count comes out to be 11, so this is a positive error, it is like the measured value is more, 11 is greater than 10.001, and in the previous example the expected value was 9.999, but if the value comes out to be 9, then it is a negative error, is measured value is less. How much? Almost by a factor, by an amount of 1. Okay. So, we can have either plus or minus 1 count at max. So, this is the error that we can encounter. And then how much error we will have in frequency measurement? So, this is error in count, and error in frequency measurement will be how much? This will depend on the gate time. Okay. So, that will be plus minus 1 divided by gate time, because within one gate time we can get one extra count or one less count. So, this is the excess frequency measured, or the less frequency measured. Okay. So, let us take an example. Say, okay, this is also interesting. Let us take input frequency equal to 10.5 hertz. Okay. And we have two instruments. Okay. Two frequency meters. One has a gate time of 1 second, another has a gate time of 0.1 second. Okay. Or okay, let us take 10 second. Now, let us compare these two instruments. So, two instruments, 2 meters. This is one, this is another. In this case, how many count do we expect? Count should be equal to 10.5. In 1 second it should be 10.5, but actual count will be either 10 or 11. So, estimated frequency is how much? If it is 10 within 1 second, then the frequency is 10 hertz. If the count is 11 within 1 second, then it is 11 hertz. Okay. This is 11. So, error is how much? Error is like 0.5 hertz. So, true frequency is, so this is 0.5 hertz. Okay. And let us say in this case, the expected count should be in 10 seconds. How much? This multiplied by 10, 10.5 into 10, which is 105. Okay. And the actual count, this is an integer. So, it may be possible that we will get exactly this value, but in this case actually one edge may lie on the, if you go back in this diagram, if an edge lies exactly on this boundary, there is a chance of missing it. So, we may still have an error, but okay. So, let me change this example a bit to make it more clear. Let me say that this is the true frequency 10.51. So, then in this case the count should be 10.51, but it will come out to be 10 or 11. So, estimated frequency will be 10 hertz or 11 hertz. So, the error will be 0.51 hertz or 0.49 hertz. In this case, the count should be 105.1, but the actual count will be equal to 105 or 106. So, the frequency estimated will be how much? 105 now divided by 10 second, because now the counting time is 10 second, or 106 divided by 10 second. Okay. So, this comes out to be 10.5 hertz or 10.6 hertz. So, the error will be 0.5 hertz in this case, no, in this case 0 hertz, 0 or 0.1 hertz. True frequency is 10.5, here it is 10.6. Okay. So, here you see the maximum error is 0.1 hertz, here you see the maximum error is 0.5 hertz. Okay. So, in general this is more accurate, sorry, less accurate. This is more accurate. So, in general, so let us take another example. Say the input frequency is around 10 hertz, but it is not known exactly, not exactly known. So, it can be 9.9, it can be 10.1, so on, but it is around 10 hertz. Now, if get time is equal to 1 second, okay, then the expected count is how much? It should be 10, but actual count, this can come out to be 1 more or 1 less. Okay. Whether it will come more than the expected count or less than the expected count, that will depend on whether this is 9.9 or 10.1, etc. So, we can in general have 1 extra count or 1 less count, okay, because in this case we do not know the exact frequency. So, the estimated frequency is how much? This expected count plus minus 1, okay, divided by get time. So, I can write this as expected count by get time plus minus 1 by get time, and this is actually the error. This is the error. Okay. Similarly, if I use okay, and in this case, let me, if I put the value get time equal to 1 second, okay, then this will come out to be 1 by 1 second, which is plus minus 1 hertz. But if I have another instrument for which this is 0.1 second, then if you do this similar analysis, the error will be plus minus 1 divided by 0.1 second. This will be equal to huge 10 hertz. I mean, the input frequency itself is 10 hertz. We can have a error of 10 hertz, I mean 100% error, huge. Why? Because this has, I mean, you just see this is 1/10 of a second, and this 1/10 of a second we have only one cycle of the input frequency. So, we will have only one edge, and we can miss that edge completely, right, and if we miss that, we will estimate the frequency to be 0. So, we will have a 100% error. Okay. So, this is less accurate, this is more accurate. So, what can we say? We can say higher gate time means higher accuracy. That is what we have seen in previous examples. Okay. You wait for longer time and measure the number of cycles, your accuracy in frequency measurement will be higher. That means, and it also depends on the input frequency. Okay. Say, now let us take two cases where I have gate time equal to 1 second, okay, but I have two cases, input frequency equal to say 10 hertz, around 10 hertz, and input frequency equal to around, not exactly, it is not known exactly, it is known around 100 hertz. So, here in this case we should have a count, expected count within 1 second, how much? 10, but true count, actual count will be 10 plus minus 1. Okay. We can miss an edge, we can have an extra edge from the next or previous cycle. In this case, again, expected count is around 100, but actual count will be 100 plus minus 1. Okay. So, that means how much error do we have here? We have only 1 out of 10, 10% error. Here we have 1 out of 100, 1% error. So, 10% error, 1% error, right. So, if you estimate the frequency here, your estimated frequency will be 9 hertz or 11 hertz. Okay. So, we will have a plus minus 1. Here your estimated frequency will be 10.1 hertz or 9.9 hertz. So, you will have a 1% error. So, then another observation from this is that higher lower input frequency implies higher error. If the frequency of the input signal is low, okay, in this case, then the chance of error is higher. Therefore, combining these two facts, we can write for low input frequency, we should use long gate time. Okay. Why? Because if the frequency is low, the error is high, but by increasing the gate time, we can increase the accuracy. So, therefore, for low input frequency, we need long gate time. This actually means if the input frequency, if this is the input signal, then wait for a sufficiently long time. I mean, do not just count this much, this many, only 3 cycles. Okay. Then there is a chance of having missing one cycle or having an extra cycle. Okay. So, this is actually 1 to 2.5 cycles. So, you can get one extra or one less. But if you wait for long time or a longer time, okay, like this, starting from here up to here. So, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, almost 10 cycles. If you miss one or get extra, so your mistake is 1 out of 10. So, here 1 out of 10 error, here 1 out of 2.5 is the error. So, here more error, here less error. So, wait for long time if the input frequency is low. Okay? That is what you have to do. But then what is the problem? The problem is your measurement time will be longer. Okay? But this will lead to slower measurement. If you wait for a long time, your accuracy will be high, but your speed will be slow. Okay. So, what can we do? The alternative solution is reciprocal counting, which we have discussed before, which is similar to measurement of frequency, measurement of time period instead of frequency. Okay. So, if my input signal is of low frequency, so this is a low frequency input. Okay. So, this is a low frequency input, then I can use a high frequency reference signal. Okay, which is much higher frequency than this input signal. Okay, and I will have sufficient number of counts in one period, because this is anyway now a long time, input frequency is low and this is reference signal. So, I will have sufficient number of counts. So, I will have more counts, and in more counts, if I have one mistake, if I have one less count or more count out of many counts, that is not too much. Okay. So, therefore, reciprocal counting is the solution. Okay. So, that is why reciprocal counting is also used. It is not only used for time period measurement, it is also used for frequency measurement indirectly. If the input frequency is low and you do not want to wait for long time, then use the reciprocal counting, your error will be less. You measure the time period and then take 1 over time period to get the frequency. Okay. Thank you.